Now let us talk about the turbines, the hydraulic turbines, which are placed in a hydroelectric power plant to generate mechanical power. So first of all, we are going to talk about impulse turbines. These are the turbines which rely on impulse force to produce mechanical energy. By impulse force is something which I can explain by an example. If you hit a nail with the hammer, then a sudden spike in pressure on the surface of the nail is what is called impulse force. So you have seen in signals and system course that you generate an impulse, which is just a momentary spike which is placed on any point along the discrete axis. So impulse force is something like that. So impulse type turbines are those turbines which rely on impulse force predominantly to produce mechanical force. So normally they are such turbines are used for heads which are usually higher than 500 meters. So the pressure of water is converted into kinetic energy in the nozzle. So there is a nozzle which through which the water escapes, and the pressure of the water behind the nozzle is converted into kinetic energy when the water passes through the nozzle. This this high velocity water which is ejected from the nozzle is incident on the wheel, which we can see in this figure. This is the nozzle, and the water which is escaping this nozzle is incident on the buckets which are located on the periphery of the wheel. So these the water is incident on these elliptical buckets, and it strikes the buckets, and then it causes the wheel to rotate, and the shaft which is present in the center of this wheel that rotates as well, and then it rotates the generators. So this is a very simplified construction which is shown here. Normally you will not find such construction on any hydroelectric power plant. Normally there are multiple nozzles which are letting the water go at different places. Like one nozzle can be here, the other nozzle can be here, then the other nozzle can be here, then the other nozzle can be here. So there are multiple nozzles which are ejecting water, and uh, 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 the more water they eject, the higher the is the speed of the shaft. So in other turbines, we generally control the speed of the turbine by controlling the flow of water via the gates which are installed on the penstock. But in this turbine, a spare or a needle comes in front of a nozzle which is ejecting the water to control the amount of water which is hitting the buckets, and then in that way it controls the speed of the wheel. This wheel is generally called a Pelton wheel, and this turbine is called a Pelton wheel turbine. So in other turbines, as we are going to see in the subsequent slides, this job is done by vanes. And these vanes open and close to control the flow of water. Now let us talk about reaction type turbines, which rely on reactionary force to produce mechanical power. What is meant by this reactionary force is that it is generated as a reaction to the flow of water around the blades of a turbine. So let's assume that this is the blade of the turbine, and water is incident on this blade in the direction as indicated here. So what will happen is the shape of the blade is such that a portion of the water flows on top of it, and the portion which flows on top of it attains a higher velocity as compared to the portion which flows portion of the water flowing from the bottom of the blade. And this higher velocity results in a lower pressure on top of the blade, and on the bottom side of the blade, because of lower velocity, there is a relatively higher pressure. Due to this difference of pressure, a force is generated from the bottom of the blade to the top of the blade, and this is force is called the lift force. So if numerous blades like this are installed on the runner of the turbine, which is normally the rotating portion of the turbine, then then the lift forces which are on all of those blades will cause the turbine shaft to rotate and produce mechanical power. So this theory of explaining this lift force is also known as equal transit theory or longer path theory. So there are multiple theories which explain this behavior of the blades, and all of them are at the same time accepted, and some of them by one thought of people, and the other thought rejects them. So all of these theories are valid for now until we find a theory which completely explain this behavior. But over here we are considering equal transit theory to explain this lift force or reaction force, which is going to rotate the turbine shaft in reaction turbines. So there are two types of reactionary turbines, which is Francis turbines and Kaplan turbines, which are used in hydroelectric power plants. So Francis turbines are generally used for low to medium head, whereas Kaplan turbines are used for low heads. So by medium heads we mean heads up to 450 meters. So up to 450 meters, from 30 meters up to 450 meters, Francis turbines are used, whereas for less than 30 meters we use Kaplan turbines. Both of these turbines, we are going to see their figures in a short while. So the turbine shaft rotates partly due to kinetic energy, which is the impulse force of the water hitting the blade of the turbine. Obviously, there will be some impulse force because water is in fact impacting the blades of the turbine. However, the major part of the force which rotates the turbine shaft is the reaction force, which is produced due to pressure difference along turbine blades. So water usually enters the turbine through a passageway or casing. Normally, the water enters the turbine through a case or casing or a passageway, which is termed scroll case in the turbines. So scroll case, we are shortly going to see the scroll case of a turbine, and it leaves the turbine via a duct, which can be rectangular or circular or both even, and this duct is known as draft tube of the turbine, and then it joins the river which is downstream, and this river which is flowing downstream of the hydroelectric power plant is termed tail race. The common terminology, I am telling you, the common terminology for that water is tail race. So there are certain guide and stay vanes in which control the direction and flow of water into the turbines. So these some the stay vanes are normally stationary, but guide vanes can move about their axis and prevent or facilitate the flow of water into the turbine runner. So water rotates the blades or fins of what is called the runner of the turbine to move the turbine shaft. So as I have told you previously, the blades are mounted on a rotating a body that is called the runner of the turbine. So here I am giving you two links to YouTube videos which give animations on the working of Francis turbine and Pelton, Francis and Kaplan turbines as a whole. I encourage you to watch these videos because when I ask you, because this is now the part of your course, so you should watch these videos, and if you have any confusions you should ask me, because questions related to working of Francis and other types of turbines can come in your terminals. So these videos which I have given the links to will show you animations of working of the turbines with much details that will clear all of your concepts. Over here you can see the turbines which we have discussed previously. So on the left side we can see a Francis turbine, while on the right side we can see the Kaplan turbine. Note that the blue portion which is over here, which is termed spiral case over here, it is also called scroll case, and this is the casing which the water enters this casing via this point and it flows around this casing, and at various points along this casing and the water enters the turbine runner via these veins which are guide veins. Which are able to rotate about their axis and alter the flow of water into the turbine, and thereby controlling the speed of the turbine. This Francis turbine is also known as radial flow turbines because, as you can see here, that the water enters the turbine runner radially along the direction of radial line of the turbine runner. Over here you can see Kaplan turbines in which the water enters from the pipes, and over here we can see the guide vanes which are installed inside the pipes which control the flow and direction of water. and the water enters the runner in a direction which is parallel to the axis of turbine rotation. Hence, these types of turbines are also called axial flow turbines. And here you can see the runner of this turbine. The water flows around it and creates lift force and impulse force as well, which rotates the turbine runner. And here you can see the draft. In this turbine, you can see the draft tube over here. Now, let us, after all of the previous explanation, now let us take a look at the overall schematic of a hydroelectric power station. Note that this schematic is produced by the author of the book and building on whatever topics he introduced in that book, but in our lectures we have covered some more topics as well. To produce a diagram in your papers which is complete in all respects, you have to have the knowledge of everything we have learned up till now. So if I ask you to create the schematic arrangement of hydroelectric power station, and you show all of the details which we have covered previously, then I will give you maximum marks. Let's say this diagram has 10 marks, then I will give you 10 marks if your diagram has all of the details and you capture those details perfectly. Or if you make this similar diagram, then you are expected to get somewhere around 70% marks. So 7 marks out of 10 you will get for recreating this diagram. But if you create a diagram from the information which I have given you in these lecture series, then you will get the maximum amount of marks. You can create those diagrams and show me if you want to see if your diagrams are correct or not. So let us start with this diagram. So water from catchment area is collected in dam, which forms the reservoir. This is pretty obvious. So the water from the catchment area, the area where you catch the water and divert it to the dam. Water from that catchment area flows into the dam, forming a reservoir. And over here, this reservoir is also the forebay. So a pressure channel or tunnel takes the water to valve house at the start of the penstock. So there is a pressure channel which is as its name indicates, because water flows in that channel under pressure. This pressure channel takes the water to the from the dam to the valve house, which is located at the start of a penstock, and surge tank is installed on top of this pressure channel. So previously I've told you that this penstock that the surge tank is installed on top of penstock. That is wrong. The surge tank is in fact installed on top of a pressure channel which is leading up to the penstock. So just keep this in mind. So the valve house contains Swiss valves and automatic isolating valves. So these two valves have different purposes. So sluice valves are there to control the water flow in the penstock, while automatic isolating valves are there to stop water flow if penstock is ruptured. And these isolating valves can also be butterfly type valves. So after this, if you look at the diagram, then after this we have a huge steel pipe. We are assuming that in this case the head is higher than 30 meters. So there is a huge steel pipe that takes water from valve house to into the powerhouse. It is also called the penstock. This is the huge steel pipe which is taking the water from valve house into the powerhouse. Powerhouse contains hydraulic turbines and alternators to convert hydraulic energy into electricity, which is obvious. So water will enter the powerhouse into the turbines, which will rotate and rotate the generators, and the generators will produce electricity. The surge tank, which is installed on the pressure channel, protects the penstock from bursting if turbine gates are suddenly closed, or imploding if the gates are suddenly opened. So and this is we have already discussed before. The only thing which was wrong in the description of surge tank was that it is located on penstocks. Rather, it is located on the pressure channels which leads up to the penstock. So the water level inside this surge tank is allowed to fluctuate. So this water level, if water is required in the pressure channel, then and in the penstocks, then the surge tank provides this water. And if it is the pressure inside the penstock is too high, then water rises into the surge tanks, and the pressure is relieved from the penstock. The governor controls valves inside the valve house. So governor is any controller which controls when the valves will open, when they will close, when how much they will open. The governor is that object, which is it is also obviously located inside valve house. It does so in response to varying load on power station.